Dear students, today we will start our second chapter, that is electrostatic potential and capacitance. In the previous chapter we have learnt about the electric field due to a charge configuration, and it is represented by a vector quantity E, that is electric field intensity. In this chapter we will represent the electric field by using a scalar quantity called electrostatic potential. What is electrostatic potential and electrostatic potential energy? In class 11 you have studied about the gravitational potential energy. What is potential energy? Potential energy is the energy due to position or configuration. How we have derived the expression for potential energy of a spring, potential energy of an freely falling body. When an external force does work in moving a body from one point to other against a force like spring force or gravitational force, that energy and that work done is stored as its potential energy. Similar to the potential energy of a mass in a gravitational field, we will find the electrostatic potential energy of a charge in an electric field. And electric potential is a quantity which gives the degree of electrification of a body, and it will decide the direction of flow of charge. A charge always flows from a higher potential to a lower potential. Before defining it, I will give some analogy by which you can understand better what is electric potential. Let us take two beakers A and B which are filled with water. In beaker A, water is at a higher level, in beaker B, water is at a lower level, and the flow of water is stopped by a stop curve. When you open the stop curve, the water flows from beaker A to beaker B. Why water is flowing? This is due to the difference in level of water in both the containers. Similarly, if you take two charged bodies which are kept in contact, the charges will flow. When two charged bodies are kept in contact, then the charge flows from higher potential to lower potential. So, to define electrostatic potential energy, let us consider a positive charge plus Q is located at the origin. So it will have an electric field surrounding to this charge Q. Now I will take one point A. At point A, which is at a distance r from plus Q, suppose a test charge, the small q, is placed at point A. So it will experience a repulsive force as both the charges are positive, If you want to move the charge plus Q from point A to point B, some work is to be done against the repulsive electrostatic force. That work done in bringing the charge from point A to point B is stored as its electrostatic potential energy. And here you should remember the charge plus Q should be very small so that it will not affect the configuration of charge plus Q. And the external force applied must be equal to the electrostatic repulsive force provided by the charge plus Q, so that the charge plus Q is not accelerated. Its kinetic energy should not increase. When the charge plus Q is brought to point B and it is left, then what will happen? The electrostatic force will take the charge to point A, thereby conserving the total energy. Now let us calculate what is the amount of work done to take the charge Q from A to B, that is WAB, that is equal to integration F external dot dr, that is also equal to the negative of the work done by the electrostatic force. Now I can write WAB is equal to UB minus UA. How this is? Because inside the electric field, if a charge Q is placed at point A, the charge Q has some energy. At point B, the charge Q has also some energy. When it is moved from A to B, its energy changes by an amount equal to the electrostatic potential energy difference, that is UB minus UA. That is equal to, this is the potential energy difference. Now this equation defines the electrostatic potential energy difference in terms of a physically meaningful quantity, that is the work done. Now how this is defined? The electrostatic potential energy difference between 2 points A and B is defined as the amount of work done in moving a charge from point A to point B against the electrostatic forces without acceleration. So now the potential energy difference is important, not the electrostatic energy at a point. It is the electrostatic potential energy difference. The electrostatic potential energy at a point is not relevant. So now we have the freedom to choose a point where the electrostatic potential energy to be 0. So we can choose point A is at infinity and the potential energy at UA is equal to 0. So we can write WAB is equal to UB, not WAB, W infinity B. So now we can define the electrostatic potential energy of a charge due to a charge configuration is the amount of work done to bring the charge from infinity to that point without acceleration. I repeat, the electrostatic potential energy at a point, the electrostatic potential energy of a charge at a point due to a charge configuration is the amount of work done to bring the charge from infinity to that point against the electrostatic forces without acceleration. So W infinity B, that is equal to UB, because UA is equal to 0. So this way we can define the electrostatic